Okay, so I've had a bit of an issue with iDrew. So today's webinar will be done on Miro. Yes, hello, Wade, hello, everyone. Just give me a moment. Okay, so I'll put up the chat and let's get to it. Okay, I'll share my screen. Share my screen. Right. Okay, so this is physics, and um, it. I've done a webinar on lenses. So today we'll be focusing on curved mirrors. Okay, so lenses are somewhat present in the A-level program. However, the curved mirrors are not. So this is an extension on the A-level topic. So sorry, I couldn't copy over because this keeps happening. Connection lost. Not sure. I think their server is down. Okay, connection has reappeared. So I'll just copy the question. I didn't have enough time to copy the question over to Miro. Okay, and now it's working. Okay, let's try doing it here. So then I'll copy the final question. So only 5 questions today. Oh no, 6. Wait a second. Oh, okay. I'm gonna risk it. That's problem 6. And has problem. What is it for mirror point source A? Well, that is L equals 12 meters away from the mirror. Okay, that should work, hopefully. Right. So, to question 1. AB is an object, and A1B1 is the image. By adding construction lines, determine the position and focal point of the curved mirror. Is it a convex or concave mirror? Well, let's have a look. Let's have a look at what we know about curved mirrors. So I'll copy this over from the assignment. So what interesting rays can we do? We need to find where the mirror is, and we need to find where the focal point is. From A to, absolutely. Well done, Thomas. This is the third interesting ray. So it goes from Q to Q prime, and it reflects on itself. So this line. And this is always perpendicular to the mirror. That's a very good line to start with. So we take a line, we join the 2 dots. Okay. And this line will be perpendicular to the mirror. Let's extend the principal axis. It's likely that our mirror is going to be on the right. I mean, but it looks that way. So this is the principal axis. Now, what else can we do? What else can we do? Well, the ray number 4, look at it. So it goes from Q to the mirror. Okay. From Q to the mirror, and it reflects at the same angle. Reflects at the same angle. So if we place a point symmetrical to Q here, let's call it Q prime, then the light would go like this and reflect and pass through this point. Okay, yeah, that is fine. That's fine, Abate. So we're going to do that. We're going to place a point. We're going to place a point. So we're going to measure this distance. So in real life, you would use a compass. And you measure the same distance down. And here's your point A prime. So a point A prime is symmetrical to, actually, why would I delete that? Symmetrical to A. And that line passing through A1, where it crosses this line, and then if it's reflected back, you can see that if it goes like this and then reflects like this, and this is another ray. So it is a ray, so we can draw it. It goes from A and then goes like this. Another ray. This ray goes like this, and then somewhere it reflects and then goes back. Then what we have here, because this is the point where ray goes like this and reflects. So, and then also here. So this is the center of the curvature of the mirror, C. So this is the center of the sphere. This is the center of the sphere. And now all we need to do is draw a circle from here. And this is a point on the mirror. This is a point on the mirror. Let's call it, okay, let's call this O. It's the center of the sphere. And this is C. And this is C. And all we need to do now, because this is the center of curvature, because we know that this line is perpendicular. This line is a radial line. And this is obviously a radial line, OC. So all we need to do is draw a curve of radius OC. Okay. And this is our curved mirror. This is our spherical curved mirror. All right. Now, we need to determine whether it is a real image. Well, it is a real image because rays actually cross there. So it is a real. The mirror is concave. So it's shiny on the left side. Concave. And it's diminished. And of course, to find the focal point, you just need to find the midpoint of OC. I hope you know how to find the midpoint using construction lines. So to find the midpoint of OC, this is the focal point. Okay, so by construction, we have drawn the mirror by having only the object and the image. Okay, so I think it's quite cool. So from only having the object and the image, we've got a lot of information. It is a real image, it's a diminished image, the mirror is concave, we found the radius of the mirror, we found the focal distance, we found the position of the mirror, and of course the focal point. Okay. Now the next problem is almost identical. AB is the object, and by adding a construction line, determine the position and the focal point of the curved mirror. Is it a convex or concave mirror? So same idea. Now, the first thing is we draw. So what do we do first? The solution is almost identical to the first one. Can somebody help me? You can use the microphone. We would love to hear from you. What do we draw first? Well, there are 4 interesting rays, 4 important rays that you can draw. Parallel and through the focal point, reflection. Well, 4 is not really suitable for us, not yet at least. 3 would be the easiest. Okay, so we draw the first ray going from here and here. So this is the third ray. And the point of intersection of the 2 lines of the principal axis, and this is the center of curvature, because both lines are perpendicular to the surface of the mirror. That means that so light goes like this, and then reflects from the mirror back to B1, and here the same thing, back and reflects back. So this is the center of curvature. Let's call it O, center of the mirror. Okay, so we use the first ray. Now, in a similar fashion, we need to find where on the mirror, because we know that if we have a mirror like this, the reflection from this point is going to be as if it was from a flat mirror. If we kind of zoom in, this section is a flat mirror, is a plane mirror. So we are pretty much reflecting from a flat mirror at this point. Flat mirror. Okay, so, and to do this, I'm going to use the same principle. So I draw a line, AB, and then I go down. Okay. So if there is a mirror, it would reflect, it would go through, the reflection would go through, this is B prime, it would go through B prime, B. thus we found the position of the surface of the mirror, because we know that light goes like this and reflects like this, because the light should be coming as if it is coming from B1. Yeah, B1 is the image, so the light is coming from the image, and we know that a mirror placed here, a mirror placed at this point, would reflect the ray like this, so as if it is coming from B1. Brilliant. And this is this point on the surface of the mirror. Let's call it C. Point on the surface of the mirror. And then all we need to do is draw the mirror. The mirror has center at O, and this is the radius of the mirror. Sorry for being messy, but it's going to be a convex mirror. Convex. The image is it real or imaginary? It is imaginary because it's behind the reflecting surface of the mirror. Look, an imaginary, a real image can be shown on a screen. So a real image is where rays actually intersect. And here we see, let's draw a bunch of rays. So this one, the first ray goes like this and then goes back the same way. And then it goes like this, and then like this. So if we focus on these two rays, this one and this one, it looks as if the light is coming from B1. That's why the image of B is B1. And the image is imaginary because light does not actually pass through B1. Light does not actually pass through B1. That's why it's imaginary. Does that make sense, Josh? Imaginary. Imaginary. And also, it's behind the mirror. It kind of makes sense. If the image is behind the mirror, it can't be a real image because there's nothing there. Light is not there. Imaginary, and it's diminished. So yeah, that's about it. Okay, good. What is the minimum height of a plane mirror? Now we're talking about plane mirrors, not convex or concave mirrors. Hung on a wall such that the person can see themselves in full height. Basically, when you stand in front of a mirror, how big should the mirror be so that you can see yourself in full height? It's an interesting one. Like, you would think that you would just need to walk further away from the mirror. If you want to see yourself in full height, you would need to walk away from the mirror. But it doesn't actually work. You would still be able to see only part of yourself if the mirror is not big enough. I kind of want to do do an experiment now. I have a mirror. And the question is to test whether I can see myself in full height. I can, obviously, because I bought this mirror in order to see that. So how big should it be? Any ideas? Can you help me? Okay, we have some time to discuss. Maybe an intuitive answer would be good. Maybe an intuitive answer would be good. Or maybe somebody can help me actually drawing it. You are allowed to draw. Annotate. Half the height of a person. How come? How come, Maya? Depends on how far you can go away from the mirror. Well, but yeah, but then again, okay, do an experiment. Your phone screen is pretty much a mirror. Okay, your phone screen is pretty much a mirror. So try positioning yourself so that you can see your full height. Can you see yourself full height in the mirror? Of course, we're looking directly at it. I mean, if we look from top, yes. If you place the phone screen like this, you can see yourself in full height. But we're talking about the mirror is on the wall, so it's like this. So Maya, I think you're onto something. It's definitely going to be like a fraction of, or maybe a fraction of the person. But can we? How can we? I think if you press annotate. Um, somewhere on Zoom. I think it's annotate. So let's draw. Let's draw a person. The person is. Well, it would make sense to draw the floor, or maybe not. And a mirror. So a mirror. Like this. Person in a mirror. No, can you not annotate, Thomas? Can you try? Can anyone try, please? You can do remote control. There's the mirror. There's the ground. Can be any height of the ground. Any height of the ground. Oh, Josh, excellent. Okay. You're wrong with should say the mirror of the person. I don't see how one follows and follows the other. Okay, do then an experiment. Please place your phone vertically, or if you have a mirror, so if you have a small mirror, that's brilliant. Put it in front of you, put it vertically, and try moving away from the mirror. And walk away from the mirror. Does the fraction of the body that you see in the mirror change as you move away? Does the fraction, and write your answer, does the fraction of your body that you can see change as you move away? Because surely if it changes, then you can move far away enough to see yourself, or maybe move it closer. If you move it closer, does the fraction of the body that you see change? Oh yeah, we can draw the virtual image of the person. Absolutely. Okay, I think it should be a bit smaller, but I can make my image bigger. It roughly matches yours. Okay. Oh, it's actually bigger. Okay. Yeah. Okay. The angle of a ray from their feet to the reflects back into the angle of a ray from their feet to the normal. Yeah, exactly. Back into the eyes. Ah, Josh, brilliant. Absolutely brilliant. Well done. Yeah, I think you got it. So what's the conclusion? Oh, you're drawing something. Okay. The trig. It's not trig. No, it's like triangles. Similar triangles. So, Maya and Era, you were both correct. I just wanted an explanation. Of course, yes, it is correct. So well done. Well done, Maya. You're the first one to get it right. And then Era. So yeah, because the distance from the person to the mirror is D, and the distance from the mirror to the image is D as well. And it's the same as if you're looking at an identical person through a mirror. Oh, sorry, through a window. Imagine it's not. Oh, better not do that. Imagine that this is not this is not a mirror, but it's a window, and in that window there's another you, a perfect copy of you. That's exactly the same distance, as they're in exactly the same size. That's what a mirror does. Creates an image. And now you're trying to see through that window. So these are your eyes. You have to match the amount as you can see. So if this is h, this is the height of the person, then because these are like triangles, this is d and the whole thing is 2d. These are similar triangles, and the ratio, of course, is going to be well, it's going to be h over 2. H over 2. The minimum height of the mirror is h over 2. And interestingly, the proportion does not change. Yeah, has anyone managed to do the experiment with a mirror and actually confirm that the proportion of the body that you can see in a mirror does not change no matter how far away is the mirror? Yeah, give me some feedback. Have you done the experiment? Yeah, so I can see, so in the mirror, in my sort of mirror, I can see my full head up to about here. So from the top of my head to about here. And let's see how many phones I can put. So one phone, two phones. So exactly two phones. Yeah, you see what's going on? So in the mirror, I can see from here, from here to here to my second button. And if I put my phone, it goes exactly twice, which is quite cool. Right. Yeah. So that's the answer is h over 2. This is like similar triangles. Okay, let's do a mathsy question. S1 is the real image of the point source of light, S. So S is a point source of light. S1 is the image obtained by a spherical mirror. O is the center of the sphere. What is the focal distance of the mirror? For what values of L does the problem have a solution? Of what values of L does the problem have a solution? So, okay. Right. What values of L does the problem have a solution? Well, we don't really know. We don't know the focal distance of the mirror, but it is a real image. That kind of helps. It is a real image. Therefore, the mirror has to be concave. Okay, the mirror has to be concave. And if this is the center of the curvature of the mirror, we can roughly draw that. Because we know it's a real image, it has to be to the left of the reflecting surface of the mirror, which is important. So the image cannot be to the right because no light can pass through the mirror. Therefore, the image cannot be on the a real image cannot be on the right, only on the left. And so light goes something like this, reflects from the mirror onto S1. Okay, that sort of makes sense. Now we have a formula for the mirror. So 1 divided by the distance to the object plus 1 divided by the distance to the image is equal to 1 divided by the focal distance. Okay. So O is the center point of the mirror. So that means that, and this is clear in the assignment, that OC is equal to 2F. What other distances are we interested in? When SO is L, that's easy. SS1 is L capital. We need S1, SC, and S1C. So SC, this distance. Okay, so it's going to be, so OC is 2F and SO is L. So it's going to be L plus 2F. And S1C is going to be, somebody help me please. S1C. Knowing that OC is 2F, because the radius of the mirror is always L plus 2F, L plus 2F minus L. Exactly. Well done, Adam. No, it's not going to be F over 2, Josh. Yeah, Adam's right. So it's going to be L plus 2F minus L capital. Great. All right, now we use this formula. And as I said, it's going to be a mathsy one. So 1 over D naught, 1 over D naught. So I'm going to type 1 over D naught. Sorry, well, D naught is the object distance, so it's going to be SC. So it's L plus 2F plus 1 over distance to the image, which is S1C. So it's 1 over L plus 2F minus L equals 1 over F. Now we find the common denominator. So we multiply the first one by F L plus 2F minus L capital. Well, actually, you know what? I'm multiplying the whole thing by F L plus 2F and times L plus 2F minus L. I'm multiplying the whole thing by that, and I get something less horrible, slightly less horrible. So I multiply F L plus 2F equals L plus 2F, L plus 2F minus L. Now, it does look scary a bit, but no worries. Just expand. F squared minus FL plus FL plus 2F squared equals L squared plus 2FL minus LL plus 2FL plus 4F squared minus 2FL. Okay, let's have a look what we can simplify. Okay, so 2F squared plus 2F squared and 4F squared, they cancel. Now FL plus L small and 2FL cancel. Is that it? Yeah, that's pretty much it. That's all that cancels. But we can see that we can do 2FL we take to the left, so FL minus 2FL FL small equals L squared minus LL. Now, why I'm taking everything F to the left? Because I'm looking for F. I'm looking for F. So F L minus 2L equals L1 minus, sorry, L minus L capital. And from here, F equals L minus L divided by L minus 2L. Now, the only thing is that L capital is greater than L small. And of course, L capital has to be greater than L small. So this value on top is going to be negative. So what are we going to do? We're going to flip it around. So it's going to be L minus L. Now we have a positive value on the top. And the bottom changes to 2L minus L capital. Now, the focal distance of a so because it is a concave mirror, sorry, because it is a real image, it can only be a concave mirror. Because if it was a convex mirror, if it would be a convex mirror, it would be like this, and this ray of light would be reflected this way. So there's no way you can have an image in this position if it's a convex mirror. I always confuse convex and concave. That's why I'm always pausing before saying that word. So F has to be F has to be greater than 0. And because F has to be greater than 0, and we know that this is positive obviously, then this has to be positive as well. So 2L minus L has to be positive. In other words, L has to be less than 2L, but on the other hand, it has to be greater than L. So the problem has a solution only if this is true. And this is the focal, and this is the focal distance. Any questions? Any questions here? I mean, the math is not particularly difficult. It's easy to make a mistake somewhere. I was lucky enough not to make a mistake. I believe so. Or at least it's the second time I'm getting the same result. Okay. So this is a useful tool. What is your cue? What is your sort of cue to use this? Well, you're not given any objects and images. The object is a point source and the image is a point source, and they're both on the optical axis. So you can't really do any construction. Construction here is pretty much useless. Okay. well, arguably you could, you know that this is the reflection and this is a normal line. So you could use the fact that this angle is equal to this angle, but then you don't know the distance. You don't know where this point is. So that's not very useful. Okay. Number 5. To create a directed beam of light, a projector uses a concave mirror of diameter 20 centimeter with a focal distance of 1 meter. At what distance from the mirror a point source of light should be placed in order to display a bright spot of diameter 40 centimeters on a wall that is 12 meters away from the mirror? Mm. Just found another solution to this problem. Okay. So how do we do this? To create a directed beam of light. Well, there are 3 possible solutions to this problem. So what like what is this? What does this even do? Well, let's find candles. If you look at old cars, this is how they did that. This is how they did headlamps. I'll show you in a minute. So this is the headlamp of a car from the 1910s probably. And you see that there was actually a candle there that is being reflected by mirrors, and this created a directed beam of light, because what you want from a headlamp is that it shines straight forward. It doesn't shine anywhere else, because you need to see in front of you. So you have a curved mirror, and you have a source of light, a candle, or well, a candle is a good example of a point source of light. Okay, so source of light. And you can have the headlamps going like this. Okay. This is how it works. And if you place a screen, so if you place a screen 12 meters apart, 12 meters away from the mirror, then you should see a bright spot. Exactly what you see when you shine a flashlight on a wall, you see a bright spot of light. Okay. If you have any questions, do let me know. But it should be quite straightforward. Right. This is another example. This is I think this is an oil burner. Yeah, it is an oil burner. So this is another model of headlamps. It used oil to instead of candles, which is kind of an advantage, more long lasting. Right. So this is the first way of doing it. The second way is like this. So this is the source. So this is the source of light. And the light goes like this. Like this. Reflects. This is the real image. So the source. This is the real image of the source. And the screen is placed here. And there's a bright spot on the screen. Okay. And another option, so option 1, 2, and 3. And 3 if we have a mirror. And we have the source of light here. Reflects. Reflects. Okay, this kept happening. So it might be that these things will disappear shortly. But anyways, and the screen is placed here, and there's a bright spot. In this case, the image is here, S1. So 3 possibilities. And here, in the first one, the image is here, S1. And in this case, this is a virtual image. So we need to look at 3 possibilities. Okay. The diagrams are not particularly accurate, but I don't want to redraw them. So I'm just going to draw that this is D. This is D. And this is the diameter of the mirror. This is the diameter of the mirror. This is the diameter of the spot. Now we know that this is 12 meters. 12 meters. And we know that what else do we know? Yeah, I was afraid of that. Okay, well, that means we can redraw the diagram. Hopefully it won't disappear this time. Okay, so we have a curved mirror. We have the source. And this is the distance to the source, A. This is the diameter of the mirror, D. And then drawing light. So this is the grid surface of the mirror. And we see the screen. The screen is here. The diameter of the spot on the screen is D. And this is A, the distance A. and the position of the image is S1. Let's call this distance B, or X. Okay, this is the diameter. And now we use the fact that these are similar triangles, which they obviously are. Okay, A, B, C, D. Using the fact that these triangles are similar, I can say that the ratio, just one more thing. The ratio of X, of D to X is equal to the ratio, this is L capital, of X plus L, of D small divided by X plus L. This is the first thing. And just a second. Okay, B's, yeah. And from here, we can find X. So XD plus LD. We can do crisscross multiplication equals XD small. So from here, XD minus D equals LD, or minus LD, sorry, minus LD. So X is equal to LD divided by D minus D capital. So I'm doing it the other way around. So this is the distance, and we can find it. The L is 12 meters. D is 0.2 meters, and this is 0.4 minus 0.2. Yeah, remember, diameter D is 20, but D is 40. So we can find the distance X, and it's going to be 12 meters. 12 meters, funnily enough. It's going to be exactly the same distance, which is the position of the image is 12 meters. Sorry, the position of the image is 12 meters, yes. But we need the position of the of S. We need the position of S. So we need A. So we're using the formula for the lens. So 1 over D distance to the object plus 1 over distance to the image, and equals 1 over F. Now, because the image is virtual, distance to the image is going to be minus 12 meters. This is important. So this is minus 12. Therefore, 1 over A minus 1 over 12 equals 1 over F, and F is 1 meter. We know that. So 1 over 1. So that's going to be 1 over A is going to be 11 twelfths. 11 twelfths. So A is 12 over 11. So slightly more than the focal distance of the lens, which is a little bit surprising to me, but I would think that it's, oh, it's plus, of course. No, no, no. It's 13 over 12. 12/13ths. So it's less than the focal distance, and that makes perfect sense. Yes, 13 meters, so that's roughly what? Yes, thank you. 12 over 13, which is 0.9 to 0.92 meters. Phew. Right, now we need another diagram for this, for the second and third option. So this is option 1. The second option is that you have a mirror, you have a source of light, S, and then light goes like this. Bam, 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 and this is the screen. This is the screen, and this is the image, S1. So light travels like this and produces an image on the screen. So this is D, this is D small, then this is the optical axis, this is L, the whole thing is L. Now this is A, and we will call this B. B is the distance from D to, sorry, from this point to S1. So let's call, okay, this is O, and this is D, so that it's less confusing. Right, so the triangles are similar. The triangles are similar, so we can write this is L minus B. This is B, and so the triangles are similar. So D divided by L minus B has to be the same as D capital divided by B. So from here, in a similar way, so BD equals DL minus DB. So B is equal to DL over D plus D. Okay, so in this case, the distance B from O to S1 is DL, so that's 0.4, 0. Wait, is it 0.2? Yeah, 0.2, and times 12 divided by 0.2, 0.2 plus 0.4, which is going to be a 1 over 3, so that's 4 meters. 4 meters. And then we use the thin, we use the curved mirror formula. So 1 over distance to the object, 1 over A, plus 1 over, now this is a real image, so it's 1 over B equals 1 over F. So 1 over A plus 1 over 4 is equal to 1. And A is 4/3, I believe. A A is, so 1 minus a quarter is 3/4. 1 over A is 3/4, so 4/3. 4/3 meters, which is 1.33 meters. 1.33 meters. Okay. So that's the distance. And finally, the third option. The third option. So we have a mirror like this. We have the source of light S. We have the optical axis. We have the screen here. And we have the light propagating here to here, from here to here. Okay, so this is 12 meters. This is D, this is D, this is L equals 12 meters, and this is S1. This distance, is B. This distance is B, and this is A. So similar triangles yet again. Similar triangles. So D divided by L. Aha, interesting. So what is this distance? So this is L. D divided by B is equal to D small. D small divided by B Yes, I have made a mistake here. I wonder where. I made a mistake. Okay, so yes, the first option is wrong. Sorry about that. Sorry about that. Because the spot of light is actually smaller, than the mirror itself. So this diagram is completely wrong. So light is traveling like this. So the image cannot be on the left. So sorry about that. So I'll just cross it out. The image cannot be on the left. So, right. So we're going to have a very similar situation here. So D small divided by B minus 12. B minus 12. And here we get dB minus 12D equals BD B minus L minus LD, and B is equal to LD over D minus D. is equal to dB d minus small d sorry. I'm getting a negative answer here, which doesn't make any sense. You can help me out here. So capital D, this divided by B, by this distance, equals small d divided by B minus L. BD minus LD is equal to BD. If I calculate, the answer is going to be negative. So what's going on? Capital. Yes. Sorry, of course. What am I saying? Yes. Yeah, absolutely. Capital D is bigger than D. That's fine. So it makes perfect sense. So 12 times 0.4 divided by 0.4 minus 0.2, which is 12 times 0.4 divided by 0.2 is 24. 24 meters. Okay, and then we use the the curved mirror formula. The object plus 1 over d of image is 1 over f. So the distance to the object is 12 meters. No, sorry, 1 over a, 1 over a plus the distance to the image is 24 meters. 1 over 24, and it's 1 over f. Okay, so from here, it's 1 on a is equal to 1 minus, so 23 24ths. So from here, a is 24 23rds. 24 23rds, which is roughly 1.043. 1.043 meters. Okay. So yeah, this problem actually has practical it has a practical application. Yeah, if you're doing lighting, for example, on a like stage lighting, you can calculate so the distance to the stage. So if you're designing a light, so you can use these formulas to figure out the size of the bright spot. And stage lighting, for example, is a lot of geometrical optics. It's pretty much mostly geometrical optics. So it's very it's important. And even stage light engineers, so the not the people who design the lights, but the people who design the stage, they do similar calculations when they are doing like where should the light go on the stage. So they mostly use triangles to calculate, but also doable. So problem 6, that's quite an amusing one. It's like it's like a house of mirrors. I don't know. Is this thing? If you have two mirrors on opposite sides of walls, you see infinite images of yourself, which is quite fun. But infinite versions of yourself. But here you have two curved mirrors. So here you have two concave mirrors. I placed a distance of 4 focal distances apart. So mirror, and that's the focal point. So we have another distance, and another. So the second mirror is here. So this is the focal point of the first mirror. This is the focal point of the second mirror. F1, F2. And into the focal point, doesn't matter which one. Let's say into this point, we place a point source of light, S. If we do it on the other hand, it's just going to be a symmetrical problem with the same solution. Point source of light, and now we draw a line. So we know that a beam coming from the focal point will go parallel and then into here. So that's going to be it's going to create an image at this point, S1. Then this image will, it's a real image, so it's going to be acting as a point source of light in this position, and it will create another image. It will create another image. To find the position of that image, so we know that this is F, this is F, this is F, this is F. We need to find the position of the second image. So we're talking about we're measuring distances from the left mirror. We're measuring the distances from the left mirror, and let it be, this be X. This is 0. This is 0. So S1 is the first image, and it has position X equals 3F. So image. Position. S1 has position to X2. So to find S2, we use the formula. So 1 over the distance to the object. Now the image S1 is now the object. And S2 is the image of S1. So S2 is the image of S1. So we can have an image of an image. More to that, we can have a real image of a real image. The real image of a real image. So 1 over the object distance, which is 3F, plus 1 over OS2. That's the position of this. 1 over OS2. 1 over OS2 is equal to 1 over f. And from here, it's quite easy to spot that 1 over OS2, so it's 1 over f minus 1 over 3f, so it's 3 minus 1, so it's going to be 1 over OS2 is going to be 2 over 3f, so OS2 is equal to 3f over 2. So S2 has position x equals 3f over 2. Okay, now S3, so 3f over 2, that's 1.5 f, so that's going to be here. So S2 is here. Now we need the we now need the image of S2. We now need the image of S2, and we have 1 over 3f over 2 no, sorry. We need the image of S2 in the right mirror. We need the image of S2 in the right mirror. So S2 is the image of S1 in left mirror. S3 is the image of S2 in the right mirror. Okay. And for the right mirror, the object distance of S2 is going to be, so 4f minus 1.5 f, so it's 5 over 2f. 1 over 5f over 2 plus 1 over x equals 1 over f. And from here, so it's 5f, 5, 3, 3f. So 1 over x is 3f over 5. Oh, sorry, that's not possible. 3 over 5f over 5f, and x is 5f over 3, but 5f over 3. Sorry, just checking something. we're measuring the distance from the right mirror. So 4f is 4f of 4f minus 5f over 3, 12, 7f over 3. Well, it's 5f over 3 from the right mirror, and also so S3 it's 7f over 3, 7f over 3 from the left mirror. So 7f over 3, that's 2. It's here. Oh, anyways, I'm gonna leave a gap here. What I would like you to prove, on your own time, if you have the opportunity, you can ask me questions next week. By the way, next week we have the same guest speaker as 2 weeks ago. So basically, the nth position is going to be so it's going to be 2n minus 1 over n times f. Okay, the nth position. I mean, it looks like the formula doesn't work, but it's because of from alternating mirrors, and you also have the duplicates of them on each of the sides. So if you have an object there, you will always have the same combination. There's going to be 3f over well, it's going to be f 3f over 2. Okay, that makes sense. Yes, because from position from the first mirror and mirror 1 and mirror 2, position from the first and from the second mirror, and this is going to be f 3f over 2, 5f over 3. So the sequence is this one, this one, this one, this one, this one. If that makes sense. The x is alternating distance from each of the two mirrors. So I would like you to prove that if you can. But this is quite an interesting thing. So the interesting concept is you have an image of an image of an image of an image, which is the same thing that you do when you're standing between two plane mirrors. You have infinite versions of yourself. All right. So yeah, that is it. That is it for today. Any questions or anything you'd like to ask? Okay.
I've got a quick question.
Yeah.
Why, when you had S, why didn't you reflect it in the right mirror? How do you know which mirrors to reflect it in?
It's going to be symmetrical. It's going to be symmetrical because if you reflect S in the right mirror, you'll get S1. Sorry, if you reflect S in the right mirror, if you reflect S in the right mirror, you get S2, I believe. sorry. If you reflect S in the right mirror, you will get this. You'll need to give it a name. You'll get this point, which is symmetrical to S2. So it's symmetrical groups of points. So what I'm doing is I'm drawing one set of points, and then they will be doubled because every point has a symmetrical. Every image has another symmetrical image.
Does that mean it doesn't matter which one you do it in? You'll still get the same result?
Not exactly. You use one mirror to get one image. But then you will have another image symmetrical to that one. So you do one mirror, and then you double the number of images. Yeah, pretty much. So you do alternating mirrors, and then you duplicate it as if you're going the other direction. So yeah. So doing left, right, left, right, left, right gives you a sequence of points in which you can write down. And then doing right, left, right, left, right, left gives you another sequence which is going to be identical to the first one in terms of it's going to be symmetrical. Okay. All right. So I'll see you. I'll see you next week. We have a guest speaker, but I will be there. And have a great week. All right. See you. Welcome.